Welcome to this deep dive, where we unpack the latest and greatest in AI research. For all of you tuning in, AI researchers, ML engineers, you definitely know the constant need to stay right on top of the field. Today, we're dissecting a brand new benchmark, MIEB. That's the Multimodal Image Embedding Benchmark. And we'll also look at its efficient sibling, MIEB Light.
Yeah, it's a really interesting piece of work.
So our goal here is to really pull out the core insights. Understand why this is a pretty significant development for evaluating visual representations, especially, as they fuel multimodal large language models, MLLMs.
Exactly. Think of this as your concentrated dose of understanding for this paper. It feels like this benchmark could really refine how we measure visual understanding in AI systems.
Okay, great. So let's maybe hit the highlights first for those needing the quick rundown.
Sure, sounds good.
All right, first insight. The current image embedding models, they show a real patchwork of performance. No single model is just crushing it across all the different visual tasks that MIEB tests.
That fragmentation is key.
Second, and this is, I think, a really big takeaway, there's a large-scale correlation study in the paper.
Yay.
It shows that Vision-Encoder Performance on MIEB strongly predicts MLLM performance when they use the same encoder. We're talking over 99% correlation on visual STS tasks.
Over 99%. That's huge. It really suggests MIEB could be a reliable proxy, for MLLM visual capabilities.
Definitely. Third point, MIEB itself, it's a substantial benchmark, 130 diverse tasks.
Yeah, 130.
Spanning 8 categories, evaluated across 38 languages. It's a really thorough look at visual understanding, even including like text within images.
That multilingual aspect is crucial too.
Fourth, for efficiency, they created MIEB Light. It's a subset 51 tasks. And it correlates incredibly well with the full benchmark. The paper mentions Spearman and Pearson correlations over 0.98.
Which is fantastic correlation for a subset.
And it massively cuts down runtime. They give an example of like an 82% saving for the E5E model.
Huge time saving, yeah.
And finally, MIEB evaluates a few types of models. Vision-only, MLLM-based embedding models, and also multimodal API embedding models.
Right.
Across all those categories we'll get into. Retrieval, document understanding, linear probing, clustering, zero-shot classification, compositionality, vision-centric QA, and visual semantic textual similarity.
Phew, quite the list.
So, yeah, the essential insights are out there. Now let's really dig in.
Okay, so that fragmented performance landscape you mentioned, it's immediately striking. We might sort of expect models to have different strengths, but MIEB gives such a granular view across those 8 categories.
Yeah.
It really underlines that a one-size-fits-all image embedding. We're not quite there yet.
Exactly. And those categories, they're designed to cover a lot of ground, right? You've got retrieval, basically matching similar stuff, visual or text.
The core similarity task.
Then document understanding, looking at whole documents, text, figures, the works.
Super important for practical apps.
Linear probing helps understand what info is actually baked into the embeddings directly.
What's linearly separable, yeah.
Clustering. Do the embeddings group related images together naturally?
Does the space make sense semantically?
Zero-shot classification.
Yeah.
How well does it generalize to stuff it hasn't seen?
Classic generalization test.
Compositionality evaluation. This sounds tricky. Understanding how visual elements and relations match the text.
Yeah, that's a tough one. Reasoning about parts and wholes.
Vision-Centric QA, inspired by MLLMs, asking questions about the visual content.
Like counting things, spatial relations.
And finally, visual STS, semantic textual similarity. Can models tell if 2 images mean roughly the same thing? Sometimes even needing OCR.
Right, comparing image meanings. And what's really valuable here is that each category is designed to probe, specific underlying abilities.
Okay.
So like good retrieval performance, that points to good cross-modal and cross-lingual matching.
Makes sense.
High scores in document understanding often mean good OCR capabilities.
Right, reading the text in the docs.
Linear probing is basically a direct readout of the info captured in the vector. Good clustering suggests a well-organized embedding space. Compositionality really pushes reasoning about visual elements, maybe confounding factors.
Okay.
Vision-Centric QA needs things like counting or object detection skills. And visual STS, like you said, can be tied closely to OCR accuracy.
So this breakdown lets you really diagnose where models shine and where they struggle.
Precisely. It's much more informative than just a single overall score.
Okay, let's circle back to that really strong correlation, over 99% on visual STS, between MIEB performance for a vision encoder and the downstream MLM performance using that same encoder.
Yeah, this finding is potentially game-changing.
Why is that? Let's unpack the significance.
Well, think about how you typically evaluate a vision encoder meant for an MLLM.
You probably have to plug it into the MLLM, right?
Yeah.
And then run a whole bunch of MLM benchmarks. Exactly. You integrate it, then benchmark the whole complex system. Yeah. Given how massive these MLMs are and the training involved, it's incredibly resource intense. It takes a ton of time and compute. Yeah, it's like checking if flour is good by baking 50 different kinds of bread.
That's a great analogy. What MIEB suggests is maybe you don't need to bake all 50 breads. By evaluating just the vision encoder, the flour, on MIED, which is way less computationally demanding, you can get a very reliable prediction of how it will perform when it's actually part of the MLLM bread.
Especially for certain tasks, like that visual STS correlation indicates.
Right. That super high correlation implies that if your encoder is good at understanding semantic similarity between images in MIEB, it's highly likely the MLLM using it will also be good at tasks needing visual understanding.
Okay, so this could mean much faster iteration, faster development cycles for vision components.
Potentially, yes. More targeted development of visual representations specifically for multimodal use cases without the massive overhead of full MLLM testing each time.
That sounds like a huge efficiency gain for researchers and engineers. Now let's talk more about MIEB itself. 130 tasks, that sounds incredibly thorough. Give us a sense of the scope.
It really is designed to be broad. We've mentioned the 8 categories, but within those, there's a lot of diversity. Diversity in the specific tasks, the modalities involved. You've got image to image, image to text, text to image, even these complex interleaved image and text queries looking for interleaved documents.
Wow, okay. All combinations.
Pretty much. And crucially, the linguistic diversity. Evaluating across 38 languages is a major component.
38 languages, right. That's vital now.
Absolutely. If you take retrieval again, you'll find tasks testing image similarity, sure, but also image text image, those interleaved scenarios, and often doing it multilingually.
So it's really pushing the boundaries there.
Definitely. Table 1 in the paper lays this all out really clearly, task by task, language by language.
And then we have MIEB Light, the leaner version. What was the motivation there? Just speed.
Primarily, yes. It was a direct response to the computational cost of running the full MIEB. It takes a lot of GPU hours. So the researchers did this analysis, looked at how models performed across all 130 tasks, and they found clusters, groups of tasks where models tended to rank similarly.
Ah, okay. So some tasks might be testing similar underlying abilities, more or less.
Kind of, yeah. Or at least discriminating between models in similar ways. So they selected a representative subset of 51 tasks from these performance clusters to create MIEB Light. The goal was a much faster evaluation that still gives you a really accurate picture of a model's overall strengths and weaknesses.
And did they pull it off? Does it actually save time and stay accurate?
It seems so. The paper shows significant runtime savings, that E5V model example you mentioned earlier, going from 264 H100 hours down to just 46.4 hours.
Wow, that's 82.4% reduction. That's massive.
It really is. And importantly, despite cutting down the tasks so much, the performance on MIEB Light correlates extremely well with the full MIEB.
Right, those high correlation numbers. 0.992 Spearman, 0.986 Pearson, across 38 models.
Exactly. So the takeaway is that MIEB Light seems to be a very reliable estimate of full MIEB performance, but at a fraction of the computational cost.
Which makes it super useful for, say, quicker model comparisons or iterating during development.
Precisely. Much more accessible for many teams.
Okay, let's dive a bit deeper into some specific task categories. Help us really understand what they're testing. Retrieval first, we touched on it, but what are the key dimensions?
Sure. So retrieval, fundamentally, it's about how well the embeddings capture semantic similarity. MIEB's retrieval tasks push this along 3 main axes. First, modality, like we said, all the combos, I, and even the complex it scenarios.
Interleave text and image, right?
Yeah. Second, multilinguality. Many tasks involve content in those 38 languages, testing if embeddings bridge the semantic gap across languages, even text in the images.
Okay.
And third, some tasks, especially VQA-related ones, use instructions in the text query to guide the model.
Ah, so it tests instruction following too, in a way.
In a sense, yes. The main metric is NDCG at 10, how well it ranks relevant stuff in the top 10. But they also use recall at 1 or map at 5 sometimes, depending on the specific task's needs or history.
Got it. Next, document understanding. Seems critical for real-world stuff.
Totally. This category is all about understanding whole documents, often with text, figures, tables mixed together. Think scientific papers, reports, things like that.
Right.
The evaluation works like retrieval, give a text query, find the most relevant document image. They use NDCG at 5 here, focusing on the top 5 results.
And this inherently tests OCR you mentioned.
It often does, yeah, because accurately reading the text within the figures or tables or main body is often crucial to know if it's relevant to the query. Table 1 explicitly flags OCR abilities here.
Okay, clear. How about linear probing? What are we probing for?
So linear probing is a way to see what kind of high-level information is readily available or linearly decodable from the embeddings. You free the pre-trained embeddings, don't change them, and train a very simple linear model, usually logistic regression on top.
It's just a linear classifier.
Exactly, to predict class labels. How well that simple model does tells you how much class information is already sort of organized in the embedding space in an easy-to-access way.
And MIEB uses few-shot probing.
Yes, default is 16 examples per class. Much faster than training on full data sets, good for a big benchmark. They mention it's often just called classification in text embedding work, and they use that term in the code too.
All right. And clustering, how is that evaluated?
They use standard K means clustering. K is set to the actual number of classes in the data set they're using for that specific task.
Okay.
Then they measure how good the clustering is using NMI normalized mutual information. It compares the clusters the algorithm found with the true labels.
So high NMI means the embeddings group things together meaningfully.
Exactly. It suggests the embedding space reflects the underlying semantic categories well, that similar things are close together.
Makes sense. Now, compositionality evaluation. This sounds like it gets into deeper understanding.
It really does. This tests if the model understands how objects, their attributes, and their spatial relationships combine to match a text description. It's about the whole picture, not just parts.
How do they test that?
Often using hard negatives, they take a correct image-text pair and subtly change something, maybe swap object attributes, change the spatial relation described in the text, or even just word order.
So can the model spot the subtle difference between the correct description and the slightly wrong one?
Precisely. MIEB calls this image-text pair classification in their code, as it's often evaluated on these pairs. The metric is just accuracy. Did it pick the right one? It's about reasoning with potentially confusing elements, not just recognizing objects.
Okay, that's definitely a step up in complexity. Vision-Centric QA. Inspired by MLLMs, you said.
Yep. Think tasks like counting objects, understanding spatial setups, is the cat on the mat, maybe even recognizing art styles, things MLLMs aim to do.
How is it framed in MIEB?
Interestingly, as retrieval, you get a question about an image, and the corpus to retrieve from is just a small set of potential answers provided for that specific question.
Clever reuse of the retrieval framework.
Yeah, makes the evaluation pipeline consistent, like asking how many curtains, and the options are 1, 2, 3. The model retrieves the best option.
Gotcha. And visual STS semantic textual similarity between images. How does that work?
The goal is to measure how similar two images are in meaning. The textual part often comes from how the ground truth similarity is established, maybe based on human judgments or associated captions. And sometimes, as we noted, understanding text within the images is key to judging their semantic similarity correctly, hence the OCR link again.
So it's about capturing the overall message or scene meaning.
Exactly. Can the model tell if these two pictures are conveying a very similar concept or scene? E5V apparently does well here.
Okay, last category deep dive. Multilingual retrieval. 38 languages is impressive. What's the key challenge here?
It's really about bridging that gap between visual content and text across many different languages. There are 55 subtasks covering those 38 languages, and the paper really highlights a key finding. You need a strong multilingual text encoder underneath it all.
The text understanding part is critical for cross-lingual image retrieval.
Absolutely. Models like E5V, which builds on AlavaNext and uses LoRa fine-tuning, perform very well. Siglip's multilingual version 2, and Vista models using the BGE M3 text backbone.
So the quality of the text encoder really matters here.
Immensely. Table 3 in the paper shows model performance across different languages, and it really drives that point home.
This paints a really comprehensive picture of MIEB. So what kinds of models did they actually test using this benchmark?
They looked at 3 main groups. First, vision-only models. Think self-supervised ones like MMOCO v3, Dino v2. They aren't trained on fixed object categories like older ImageNet models.
Okay, self-supervised visual learners.
Second, MLLM-based models, which are inherently multimodal.
Right, designed for image and text from the start.
And third, Multimodal API embedding models. The Voyage API is the example they give. These are often tuned for specific business applications, like understanding figures and tables in documents.
Interesting. How did they handle inputs that mix images and text?
If the model had a native way to handle interleaved input, they used that. If not, they defaulted to a simple sum of the text and image embeddings to create a joint representation.
A practical approach.
Yeah.
So running these different models through MIEB, what were the big findings? Any surprises?
Yeah, quite a few interesting points. For overall retrieval, CLAP, VIT big, and a SIGLET variant came out on top.
Okay, strong CLIP style models.
But MLLM-based models specifically excelled in the interleaved subcategories, like VQA retrieval, which kind of makes sense given their architecture.
Right, but they struggled elsewhere.
They seem to find clustering tasks more challenging generally.
Interesting trade-off.
E5V really stood out for multilingual retrieval and visual STS, likely due to its multilingual training data and NLI collections.
Okay, what about OCR-heavy tasks like document understanding?
Textually supervised models, like CLAP variants, generally did better on tasks needing OCR compared to purely visually supervised ones. For document understanding specifically, E5V was the best open source model, but the closed source Voyage Multimodal 3 performed even better.
Ah, the specialized API model shines there.
Seems so. And compositionality evaluation, still really tough for most models.
That remains a frontier then.
Definitely. One surprise was BLIP models doing well in Vision-Centric QA. The author suggests maybe including images during contrastive fine-tuning helps particularly for those kinds of tasks.
Huh, interesting nuance. And there's a leaderboard.
Yes, Table 22 has the first MIEB leaderboard, though it only includes models they could evaluate on all tasks.
Good context. It really shows how different models have very different profiles across these diverse tasks.
Exactly, that fragmentation again.
And just to underscore the efficiency point one more time, MIEB Light really does offer significant savings.
Oh, absolutely. That reduction is substantial, as we discussed. Table 5 shows it clearly, often over 70–80% reduction in GPU hours.
Using E5V as the example, 264 hours down to 46.4.
Right, and for a smaller CLIP model, it was still over 70% savings. That efficiency, combined with the high-performance correlation, makes MIEB Light really practical.
Yeah, very appealing for faster dev cycles.
Yeah.
Finally, how does MIB stack up against older benchmarks? What's its unique contribution?
Well, it seems to directly tackle limitations of prior benchmarks. Many older ones focused more narrowly, maybe just on classification and basic retrieval.
Okay.
MIB brings much broader task diversity, things like multimodal compositionality, social media understanding, that extensive multilingual evaluation. These are often missing or less developed elsewhere.
Now the focus on visual text.
That too. OCR, visual document retrieval, crucial for MLLMs, but not always central in older image embedding benchmarks.
Right.
Plus, it evaluates instruction-tuned embeddings beyond just retrieval, looking at how they generalize across more tasks. So by bringing all this together, 130 diverse tasks, MIEB aims for a more holistic, insightful evaluation standard.
This has been a really fantastic deep dive into MIEB. It feels like a genuinely useful and comprehensive tool. It clearly highlights the different strengths of models, and crucially, that strong link between encoder performance here and downstream MLLM success. And MIEB Light seems like a very practical, efficient way to get a good sense of that performance.
Absolutely. And thinking about where this leads is, I think, quite interesting.
Okay, so let's leave our listeners with something to chew on. For you listening AI researchers, engineers, here's the thought. Given this really strong correlation they found, especially on tasks like visual STS, how might future vision encoders be designed differently? Could they be specifically optimized to ace benchmarks like MIEB, knowing it likely boosts MLLM performance?
Right, could MIE become a direct target for optimization?
And also, what are the practical implications for your work? Knowing that certain models excel at, say, document understanding, while others are better at compositionality, how does that influence model selection for specific applications?
These are definitely the kind of questions that MIEB helps us frame and hopefully answer better going forward. It could really guide more targeted improvements in visual representation learning.
We definitely encourage you to check out the full paper, explore the MIEB leaderboard online. There's a lot more detail in there.
For sure, understanding these evaluation tools is pretty vital for anyone working in this fast-moving field.
Couldn't agree more. Well, that wraps up this deep dive. Thanks so much for joining us.
My pleasure.
And we look forward to our next exploration into the cutting edge of AI research.